So now, once we have initialized both the matrices, then we can go ahead with the our algorithm. So how we define the Flood Warshall algorithm. So the input is this W matrix, okay, and we can identify the length or the number of nodes by reading, say, the number of rows of this matrix, okay. So we can say n is the number which is defining the size. Will always be a square matrices because number of rows and number of columns are equivalent to the number of vertices. That is, say, I can take, say, rows of W, okay. That's the number of rows, okay. So this simple function, say, fetch the number of rows of W, and that is being stored in n. Now we have to initialize our initial matrix. So at each step we calculate a matrix. So at the 0th step, if I say I'm calculating the matrix value, so this is the 0th step. So I'm naming it, say, M0, okay. And I'm defining M0 is equals to this initial weight matrix, which is W, okay. So this is how I have, say, initialized the matrices here. Now the same way, the parent matrix can be initialized. So if I name it, say, pi, okay, the size of this matrix is again equivalent to the size of the matrix W, okay. So you can initialize pi is equals to np dot zeros to piw, or in any other way where you want to, say, define the size of the matrix of pi, okay. Now in pi matrix there is a simple computation that I can go for I is equals to 1 to n, and for a is equals to 1 to n, and here we can say pi I comma j, okay. So it will be defined in two ways. If this value, there is a path in W, okay. So if W I j is not equal to null or infinite here, okay. If Wij is not equal to nil and I is not equal to j, in both the condition we can say Pij is equals to I. If this condition doesn't follow, so that means either I is equals to j or Wij is equals to infinite, then we can initialize Pi I comma j is equals to nil. Okay, this is what how we have defined it in the matrix above. Okay, so when I is equals to j, that means 4 comma 4, it is all nil. If the value is infinite, then also the value is nil. Okay, otherwise it is same as the row number, so that is equivalent to I. Okay, so this is how we define the initialize the weight matrix and the parent matrix, okay. And similar to weight matrix, here we can define maybe the size again also. Consider that we don't know size, okay, or number of vertices in the beginning, and the only input we get is say the matrix here. Okay, so the number of rows of W will be n, and then we can go in this loop. Okay, now coming to Flood Warshall algorithm. So how to move ahead? So this is a very simple algorithm where we can define one parameter, say k. So we generate k matrices here, okay, from 1 to n, and k is again equivalent to the number of nodes. Then for I is equals to 1 to n, and for k is equals to 1 to n. So that means k number of time, and for I, when I say 1 to n or j is equals to 1 to n, that means I'm moving in this matrix. Okay, so this matrix has say n square number of elements. To reach any of the element, I can go from 1 to n and 1 to n in the both rows and columns respectively. Okay, so I am defining the matrix m k. Okay, so at every step I'm defining a matrix mk, and mkij will be equals to, okay, let me just take it to little left, so it will be not too big, but still I better, more space is better, so that I can represent it in one line. So minimum of either the previous entry now will come from the previous matrix. So the previous matrix is m k minus 1. Okay, so either the value in the previous matrix, this is k minus 1 ij, or otherwise if we are making kth node as an intermediate node. So the meaning of the intermediate node here is that instead of moving from I to j, I can move from I to node k, and from node k I can move to node j. Okay, so instead of moving from I to j directly, I'm checking if I put k as an intermediate node. So that means you are first moving from I to k and then k to j. So if this value is lesser than the value of reaching directly from I to j, then we will update this value. Okay, and since we have already initialized pi matrix in the right hand side, okay, so you have to first execute this algorithm, and if we have we are ready with this algorithm on the right hand side, then we can update the parent also. Okay, so this is the say the algorithm where we say finalize it, say minimum of these two. Okay, but to identify minimum of two, you have to put one condition, if condition, right? So I can put that if condition directly here. Okay, so let me put that condition here. So I put if the left hand side part is greater than, or maybe say less than, equals to the right hand side part. Okay, so if this is true, then my matrix m superscript k. Okay, so this is what kth matrix we are defining. So what I'm writing right now and what I had written earlier, both are same. So if you can go with either, it is fine. Okay, so we always want to store the minimum of the value. So if the left hand side is minimum, then that will get stored in the matrix. Why I have utilized this here? Because in the right hand side we have defined the parent matrix. Okay, and this can also be say superscripted with say the initial matrix, which I am saying pi0. Okay, so pi 0. Now, in left hand side, we can define the upcoming version of pi, which is say pik, which will be equals to, okay, now obviously I comma j index we want to store I comma j here, okay, and similarly I comma j, okay, will take the same value as of its parent. So, okay, did it. So this will take the same value of as of its previous part. So that is pi a via superscript. So this will be left hand side entry will be equals to pi k minus 1 ij. Okay, so this is same as of the previous matrix. However, if this condition breaks and we go into the else statement, then these two statements will change. Okay, so now if I want to define the my matrix mkij, it will be equivalent to the right hand side part portion of the comparison. Okay, so that would be the value of mi to k plus k to j. Okay, similarly the pij matrix will be now will take the value which is equals to the value of pi k to j. Okay, so that means you have to first reach to k and then k to j. So instead of first we were reaching I to j directly, now we are reaching from k to j. Okay, so this is how we update the parent matrix. Now these two parts are very important, and I guess most of the videos they miss this part, so I'm highlighting. This is pth matrix and this is the update. Okay, so in the end, when this all functions are completed, we can simply return the last matrices, that is, so we can return ei superscript k matrix, as well as, so this is one output, another output will be the mk. Now this kth index matrix is the last matrix which is formally can be say this matrix pik and mk is the final matrix which will provide you the shortest path between each and every pair. Okay, so this is how we define the mk matrix. Okay, so this is the maybe theoretical part where we have seen the algorithms. Okay, if we want to say analyze the algorithm, so it is say there are 3 loops all of size n. So this is n cube and n is the number of vertices here. So this is v cube. Okay, so is the complexity of this algorithm. These statements, some 5-6 statements here will definitely take some constant time. It is just adjustment of some values. Okay, so the complexity of this algorithm is equals to v cube. Okay, now coming back to the numerical part. Okay, so this is the parent matrix, and on parallel I have the, so this is the weight matrix, this is the parent matrix. Okay, okay, so this is now also the left hand side is also my m0. Okay, so this matrix is now my m0 matrix. I want to write it somewhere. Yeah, so this matrix is, okay, I can highlight maybe from the top. So this matrix is my m0. zero matrix. Okay. Now the next matrix I want to create is M1. So in order to create M1, I need to put 1 as the intermediate node. Okay, so I'm creating another video so that someone who want to directly go to the numerical portion can skip this part and can go to the numerical part directly. Okay, so let me end this video.